Okay, good morning, everybody. So we will start today the lecture on a new topic. So again, just to remind, the lecture is being recorded. So please don't walk in front of the camera and remember whatever you say is going to be recorded. All right. So today we start discussing a new topic, very important. Something called convolution. Super important thing. So convolution is an operation that is natural in nature, and there's a mathematical model that describes how convolution happens. But let's first look at what this thing is. Okay, so convolution is the fundamental operation that describes how a linear time invariant system behaves when you have a particular input, right? So to get into it, let's start with something simple. So let's go back to an LTI system. So this is a linear time invariant system, LTI system. And it has an input and an output. So this is my input. It's got a waveform xt going in to produce a waveform yt coming out. Right? It's a two-port network. This is my input. This is my output. And I said that this is LTI. So we can visualize the input and output in terms of the time domain input waveform and output waveform. But we can also visualize it in terms of the frequency domain, right? We know that if we take the Fourier transform, we get capital X of f, and we take the Fourier transform of the output side, we get capital Y of f. These are in general complex functions. So simple X produces simple Y output waveform. Capital X of f produces capital Y of f output spectrum. So input spectrum gets mapped to output spectrum. Input waveform gets mapped to output waveform, right? But the information that is contained in the time domain version X of t is exactly the same as what it's contained in the frequency domain. They are just two duals of each other. There's nothing that's in the time domain that's not already encoded in the frequency domain and vice versa. So very important thing to remember is that whether you are in the time domain or in the frequency domain, you are describing the same physical thing, physical circuit, right? It's just a mathematical model. You can model it in the time domain or you can model it in the frequency domain, but these two models are just duals of each other in terms of time and frequency, containing the same information. The system itself is just a circuit. It doesn't know whether it's time domain or frequency domain. It produces an input. It produces an output when it's given some input. That's all. So the question is, how can we predict what the output is going to be if you know what the input is, right? So if you know if you know xt, can you produce yt, right? If you know something about the system, or similarly, if you know capital X of f, can you produce capital Y of f if you know the same things about the system? So it turns out that convolution is the key to this, right? And we'll get about explaining how that works. But just to give you a preview, there is something called convolution, right? And this system has something called an impulse response. We'll come to that. An impulse response. So by convention, we call it h of t. It's just a function. It's a time function. So I can take this time function, impulse response, and compute the Fourier transform of the impulse response. And I get a corresponding frequency domain function, capital H of f. Right. So in the terminology, right, you have an impulse response simple h of t. In general, this is complex value and this is complex value. So this function is called the transfer function. Transfer function in frequency domain. So we will learn how to relate the transfer function in the frequency domain with the impulse response and how x of t, h of t, and y of t are interrelated, right? We will also learn how capital X of f, capital Y of f, and capital H of f are interrelated, and how every single thing is interrelated to each other, right? Time to time relationship, frequency to frequency relationship, time to frequency, frequency to time. Every possible permutation and combination of these things are all related using simple theory, starting with the convolution and the Fourier transform. So we'll go through all that in a very methodical way, but this is just the bird's eye view of what we are going to do. Okay, so let's take a quick photo. So let's take a simple example of an LTI system. Let's say we have an LTI system which has an input x of t. It's got 3 branches in this example. First branch is a pure scaling operation by alpha. So this is an amplifier. Amplifier or amplifier if alpha greater than 0, greater than 1, attenuator if alpha. Then we have a delay. I'm just giving you some examples of the possible things that we can have. Let's say this is delay t. And let's say we have an integrator. Sum them up. Summation block producing y of t. So 3 branches in the signal flow graph. The first branch is a pure amplification or attenuation, so that is modeled as a scaling constant alpha, right? So the gain is alpha. Second branch is a pure delay, so it does nothing to the signal except delay it by capital T, right? The third branch is a integration. Right? So we can visualize if you give a particular input into this input x, right? We set x of t into a particular function. We can find out individually what each branch is doing, and we can adapt the different components to produce the final output. We did that. So I'm going to select a particular input. I'm going to set x of t by definition as my delta function. So in the time domain, it looks like a little impulse, right? So I have my time domain. Time, it's 0 valued, it jumps up and then comes down, but we know that by definition the integral of delta t is equal to 1. So where's this coming from? We have a pulse, right? A pulse which is going like this, and we select this duration to be tau and this height A to be 1 over 2. So we know that the area is equal to A times tau, which is equal to 1 over tau times tau, which is equal to 1. And we take the limit as tau tends to 0, right? Gives you delta. By definition, this is called the Dirac delta function. So the Dirac delta function is an impulse function which has a area, that means its integral is defined as 1. So we can find the output in terms of 3 components. Here you will get another impulse coming out, that is alpha times delta t, because the only thing that happened was you scaled it by alpha. Right. This branch will have delta t minus 1 because t is the delay, so we change the variable from t to t minus t to account for the shift in time. Okay. And the third one, by definition, will give you 1, because by definition, the integral of delta t is 1. So the moment your time value passes delta t, its integral value becomes 1 and it stays at 1. So I'm going to give this function a special name, let's say u of t. Right. So my impulse response, right? The impulse response h of t is the response of the system when your input is a delta function. So we can call a special name h of t, which is when x of t is equal to delta t, right? Becomes the linear summation of the 3 components that are coming out. The first component is alpha times delta. Second component is delta t minus t. And the third component is am I good, guys? Did I make any mistakes? You're good? Yes.
Excuse me. So right down there below xt, does it say number t, right?
Where's that? Oh, here, yes. So lambda is just a temporary variable. So when you integrate x of lambda d lambda from negative infinity to t, what you pop out is a function of time.
Okay, so right here, this is basically lambda t, right?
This is the integral of lambda. So where lambda t is equal to delta t, because we chose xt to be delta t.
Okay, so xt is basically equivalent to lambda t, right?
Inside this integral. Inside here.
Okay.
Right. So x of t was selected to be delta t, but t is lambda the moment you stick this inside here, because t and lambda are just temporary variables. So when I put this input x of t inside this integral, the temporary variable is called lambda. So delta t becomes delta lambda, which is still the same.
Oh, okay.
Let's do another example. So my LTI system has alpha 1, Let's say this is delay T1. This is alpha 2, delay T2. And so on and so forth. It has m branches, alpha m, delay Tn. All the branches are summed up. So it is n minus 1, like that. And this is my output y of t. So this is an m branch. So in the time domain, I can write out what y of t is in terms of the input x of t by inspection. I go branch to branch to branch, and I can see some pattern, right? The first branch is a pure delay by t1 and the scaling by alpha 1. So my contribution from the first branch is y of t is equal to alpha 1 x t minus t1. Right. Contribution from the second branch, again by inspection, alpha 2 times x t minus t2 plus. And it goes on till mth branch, alpha m x. So what happens if I put alpha is equal to, sorry, if I put xt is given by delta t, then yt is by definition called h of t, the impulse response. Why? I set the input to be an impulse, so therefore whatever output it produces has to be the response of the input impulse, which is the impulse response. So I can write out h of t by inspection. Everywhere I have x, I have now delta because I replaced x with delta. Right. So I have alpha 1 delta t minus t1 plus alpha 2 delta t minus t2 dot 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 all the way to the last one, alpha m delta t minus t. So if you know the signal flow graph and where all the alpha 1, alpha 2 gates are and where all your delays are, you can find out what the impulse response of the system is just by looking at it. By inspection. There is no math. It looks like math, but not really, because you can just write it down in one shot. So these things look super complicated when you don't understand it, right? But if you know the trick behind it and how it came about, it's actually very, very simple. You look at every branch, look at the gains, look at the delays, and you write down the equation, one shot. Let's take a picture. So now let's see. So this is the relationship between the input and the output, right? For any arbitrary input x of t, the arbitrary output y of t can be found by inspection, looking at the signal flow graph. If the input is a special case, simple delta t, it produces the output y of t, which is now called h of t, given by that, using the same equation. The final thing that we want to do is, I want to take this first expression, right? I'll start here. So I'm going to call this expression 1, and then say from 1 taking the Fourier transform of 1. Okay. So I'm going to take the expression 1 and take its Fourier transform term by term by term. So on the left-hand side, the Fourier transform of y of t is simply called capital Y of f. So I have capital Y of f y, because y of t and capital Y of f are Fourier transform pair, right? That's one, which is equal to, I take the Fourier transform of every term. So the first term is alpha 1 x t minus t1, right? So if the Fourier transform of x of t is capital X of f, we know that the Fourier transform of alpha times x t minus t is simply alpha times capital X of f e to the minus j 2 by f t. We did that property of the Fourier transform. So we can use that property multiple times for every term. So for the first term, it becomes alpha 1 capital X f e to the j 2 by f t1, right? For the second term, alpha 2 capital X of f 2 by f now t2 dot dot dot. The last one, alpha m capital X of f e to the minus j 2 by f t m. So what did I do? I took every term in the output that I found earlier, right, in one. So the output consists of m terms, 1, 2, 3, all the way to m. Every term, I separately applied my Fourier transform property, which has a scaling and a delay, right? The scaling just scales the thing by whatever constant, and the delay just rotates the phase by the right amount for every case. So the scalings are different, alpha 1, alpha 2, alpha 3, which means that you have a different scaling term. The delays are also different, capital T1, capital T2, capital T, all the way to M, and it causes various amounts of phase rotation for every term. So all that stuff gets adds up and gives you this big ugly equation, which is the output transform. But this can be simplified. So when you look at this, you can see some common parts. What's the common part? Alpha 1, alpha 2, alpha m are not common, right? Phase rotation components are not common, but the transform x of f is common. So I can see this common section, I can take it out. I can take it out into a factor and write the final expression as x of f, my common section, plus the individual components, which is 1. Alpha 1 this, alpha 2 that. I can just write it as sigma k equal 1 to m alpha m j 2 by f. So I did two things in one step. I took x of f, capital X of f out, right? And then I wrote all the phase terms as a sigma, as a summation, right? It's just a summation. I just generalized T1, T2 to some Tk, and I wrote it in terms of Tk. Just add stuff up. It's a compact way of writing. Yeah.
Okay, just to clarify about something that I asked you earlier. Okay, XX, right?
That's simple X of T, yes.
Oh, okay. That's if I was a lambda.
No, it's a sorry, it's simple X of T.
Oh, okay. Thank you.
All right, so look at the stuff now. All right, so we have this component, right? I'm going to start from there. I'm going to erase this and give you the result that we are looking for. So far in the game, what we have done is we have taken a linear time invariant system, right? This has x of t. In frequency domain, it's capital X of f. Produces output y of t. In frequency domain, it's capital Y of f. Right? And its impulse response, this is a property of the system, is h of t. It produces a transfer function, capital H of f. So to get there, let's start with the equation that we derived here. So I'm going to call it 2, right? Say from 2, we now have a relationship that output spectrum, capital Y of f, in terms of the input spectrum, right? And a bunch of scaling and delays. So this is the property of the system. There is no component here that depends on the signal. It is a property of the system, right? So in this square brackets consists a complete description of what's going on inside that LTI system. It completely describes the system. Capital X of f completely describes the input, whereas capital Y of f completely describes the output, all in the frequency domain. So we can visualize this thing as a relationship between the spectrum of the input, the spectrum of the system's behavior, and the spectrum of the output. Okay? It's a spectrum-based description. So we have the spectrum of the output, right? I'm going to call it the Fourier spectrum of the output signal. Is equal to capital X of f. This is the Fourier spectrum of the input signal. Times this thing, sigma k equals 1 to m alpha k e to the minus j 2 pi f t k. So interestingly, the last term is a Fourier spectrum. Fourier spectrum that only depends on the system. On the particular system. Particular LTI system. So we have a very clean description, right? Spectrum in the output is equal to spectrum at the input times something that is independent of the input or output, but it's in a way its own description of what's inside the box. So this describes the box in the frequency domain, right? So this is basically a description of that. Okay. We have a thing, a mathematical expression in the frequency domain with variable f describing what's going on inside the box as a parameters of the amplifiers and the delays, right? It's got nothing to do with inputs and outputs. It's just even if there was no input or output, this part would still remain as long as you have your circuit in your hand, right? This is something that's input dependent, with which we provide externally, and the net result of both these things produces y of f. So everything is in the frequency domain right now. So we call this particular expression, you evaluate it, and we give it a new name. We call it the frequency domain input output transfer function. We call this h of x. So you can show very easily that if you take the input x of t and set the input to be delta t, the impulse response, sorry, the unit impulse function, it produces a bunch of scaled and delayed outputs. Each of them are impulses. So if you work the math, you will find that h of f is actually the Fourier transform of the impulse response. So we can prove that later, but think of a relationship. H of t is the Fourier transform of the impulse response. So this is it. So this is my transfer function. Transfer function. We call it TF for short, and this is my unit impulse response. So what we are really saying is the behavior of a linear time invariant system, LTI system, is completely described using simple h of t, the impulse response, in the time domain, or you can completely describe it in the frequency domain by taking the Fourier transform of the impulse response, which is called h of f, and it takes this form for LTI systems of that time. Okay. I have ignored differentiation and integration for now to keep things simple, but you can extend this derivation to cases where you have delays, scaling, integration, and differentiation. But we'll do that at a next level. For now, let's only consider delays and scaling. So what do we get? We have, I come over here. Let me erase this. Get a pen. So I have y of f is equal to x of f times sigma k equal 1 to m alpha k minus j 2 pi f. Okay, right? I call this guy h of f. So I get x of f times h of f is defined as therefore the Fourier transform of the impulse response function h of t, which is h of f, is equal to the output of the spectrum divided by the input. So I can write this as h of t, Fourier transform gives me h of f, which is the same thing as y of f. So this is the ratio of input spectrum, input and output spectrum. So this is the input side, and this is the output side. So stated in a different way, if you don't know what's inside this box and you want to find out what's inside, you can apply some known spectrum at the input, measure the spectrum at the output, and you divide those two spectrums by, output divided by input and get a complex function out. And that is directly by measurement h of f. So once you measure that, you can find the inverse Fourier transform and find h of t. No problem. So next we come to the topic of convolution, which we will cover in detail in the next couple of days. But I will only introduce you the basic concept right now. So let's erase. And you get all the notes by me. So if you don't write it down right now, don't. So to understand how convolution works, we have to first define it. So we will first define the operation of convolution in the continuous time domain. Convolution, continuous time. So if you have waveforms, let's say y of t, say h of t and x of t. With output y of t. So we have this is an LTI system. We are going to say two things. One, this is impulse response is h of t, and this is a convolver. It produces a convolution. Let's say it does that. It implements a convolution. So we can write the input x of t and the output y of t, where the output y of t is defined as the convolution between h of t and x of t. Notice I put the asterisk, that's a special symbol, right? This is a new mathematical symbol that you have to pay attention to. This is not multiplication, right? This is called the convolution. But this is not multiplication. So when you look at signal processing books and you see the star or asterisk, it is, don't confuse that with the multiplication. That is a convolution, a specially defined operation that I'm going to define in the next 10 seconds. All right. So the convolution, this operation is defined like so. Xt convolution h of t is by definition the integral minus infinity to infinity h tau x t minus tau. This is dummy. Or temperature. So convolution is an integration. It goes in the limit of minus infinity to plus infinity in this time-like variable tau. It's not time, but it's a temporary time-like variable, which we use to get an output that has a function of time, right? So the output of the integration along tau is a function that is independent variable. All right, so we can define this y of t by definition. So what is the convolution operation? It's a linear time invariant operation, first point, right? So you can implement the convolution using circuits like filters. Or stated another way, if you take a filter and you describe its behavior using mathematics, what you get is a convolution. Okay. It doesn't work the other way, right? I mean, you can't make it do something. It does something, and its mathematical model is a convolution. Convolution has this particular definition in the time continuous mode. That means this is not a digital system. This is an analog system. It's a continuous time operation for this for now. It's got two functions, h of t, which is the impulse response of your system, and h of t, which is the impulse response of our system, x of t, which is the input, and it produces y of t, the output. So the relationship between the input, the property of the system, and the output is defined as the convolution. Okay? And it's defined like this in terms of the dummy variable tau, which when you evaluate the integral, this is a parameter, right? This is a parameter. Parameter is time. So when you integrate along tau and apply the limits, out pops a function which is a function of time. So I'll leave it at that and we'll continue on Tuesday. Thank you. Yes, sir.